These are the manufacturing secrets behind why some plastic packaging seems designed to torture you, and the multi-billion-dollar BOPP industry that makes it nearly impossible to open on purpose. You've been there, standing in your kitchen, wrestling with a plastic bag that refuses to tear along any logical line. You pull, you stretch, you even try to bite it open. The plastic just stretches and deforms, mocking your attempts to access whatever's inside. What you're fighting isn't an accident, it's BOPP, biaxially oriented polypropylene, and the result of precise engineering designed to create what scientists call biaxially oriented films with carefully controlled tear resistance properties. The global market for these tough plastic films reached over $22 billion in 2024, producing nearly 10 million tons of material. That's enough plastic film to wrap the entire state of Rhode Island several times over. But here's what most people don't realize: the same process that makes your packaging so frustratingly strong also represents some of the most sophisticated polymer science on Earth. Let me take you inside the hidden world of plastic film manufacturing, where molecular chains get twisted into submission and tear resistance is engineered at the atomic level. The story begins with something called polymer chain orientation. Picture a handful of cooked spaghetti. That's what polymer molecules look like in regular isotactic polypropylene. The strands are tangled, random, pointing in every direction. But during the manufacturing process, these molecular chains get forcibly aligned through a process that's part chemistry, part mechanical torture. When plastic film gets produced, it's stretched between 300 to 400% of its original size in what's called the tubular process. But that's just the beginning. In the more common tenterframe manufacturing method, the film gets stretched 4.5 times longer in the machine direction and 8 times wider in the transverse direction. Imagine stretching a piece of taffy to nearly 5 times its length while simultaneously pulling it 8 times wider. That's the kind of molecular violence happening inside these machines. After this extreme stretching, the film undergoes corona treatment, where electrical discharge modifies the surface to improve ink adhesion and sealing properties. This stretching and treatment process aligns those spaghetti-like polymer chains into neat parallel rows. Once aligned, the covalent bonds along each chain create incredible strength in the direction of alignment. It's like turning a jumbled mess of rope into a perfectly braided cable. The difference in strength is dramatic. Tensile strength jumps to between 150 and 250 megapascals, while the modulus of elasticity reaches up to 6,500 newtons per square millimeter in the strongest direction. But here's where it gets interesting. This incredible strength comes with a trade-off that packaging engineers exploit ruthlessly. While the aligned polymer chains create super strength in one direction, they actually create weakness in others. It's basic physics. The forces holding polymer chains together are much stronger than the forces between different chains. This creates what scientists call anisotropic properties, different strengths in different directions. Think of it like trying to tear a phone book. Tear it along the page direction and you'll struggle. But try to tear it perpendicular to the pages and it rips easily. Plastic manufacturers use the same principle, except they can control exactly which directions are strong and which are weak. The most sophisticated packaging uses what's called co-extruded multi-layer films. These aren't just single sheets of plastic, they're engineered sandwiches with anywhere from 3 to 13 different layers, each designed for specific properties. Some films have been created with over 1,000 layers, though that's more for specialized industrial applications. BOPET, biaxially oriented polyethylene terephthalate, often serves as a strength layer, while ethylene vinyl alcohol, or EVOH, provides superior barrier properties against oxygen and moisture. Each layer serves a purpose. The outer layer might be optimized for printability and gloss. The middle layers could provide barrier properties to keep air or moisture out. The inner layer might be designed for heat sealing. When you combine multiple layers with different molecular orientations, you create packaging that's nearly impossible to tear predictably. This is why tear notches, those little cuts or perforations meant to guide your tear, often fail spectacularly. The notch starts the tear in the right direction, but as the tear propagates through multiple layers with different molecular orientations, it gets redirected. Instead of following your intended path, The tear follows the path of least resistance through the polymer matrix, which might zigzag unpredictably through the material. The numbers behind this industry are staggering. Asia Pacific produces 58% of global BOPP film production, totaling about 5,610,000 tons in 2024. The food packaging industry alone consumes 63% of all BOPP film production. Films in the 15 to 30 micrometer thickness range dominate the market with 64% of global production. But here's the part that might surprise you. Much of this frustrating packaging design is intentional, and there are legitimate reasons for it. Retailers lose billions of dollars annually to shoplifting, and difficult-to-open packaging serves as a significant deterrent. The harder it is to quickly open a package, the less likely someone is to steal it. This is why small, expensive electronics often come in those impossible clamshell packages that seem to require industrial equipment to open. The problem has become so widespread that it has its own name: Wrap Rage. Consumer Reports magazine even created the Oyster Awards in 2006 for products with the hardest to open packaging. The statistics are sobering. According to UK NHS data, over 60,000 people receive hospital treatment each year in Britain due to injuries from opening food packaging. In the United States, the Consumer Product Safety Commission estimated about 6,500 emergency department visits in 2004 from packaging-related injuries. A British survey found that 99% of respondents said packaging had become harder to open over the previous 10 years. The most common injury was a cut finger, followed by cuts to the hand, sprained wrists, bruised hands, and strained shoulder muscles. People resort to increasingly dangerous tools, razor blades, box cutters, ice picks, in their desperation to open packages. The irony is that there's often a simple solution hiding in your kitchen drawer. A rotary can opener, the kind almost every household has, can easily cut through the straight edges of clamshell packaging. The hard cutting edge that's designed to pierce aluminum cans makes quick work of oriented plastic films. But the industry hasn't ignored the frustration. Amazon launched its frustration-free packaging initiative in 2008, setting strict requirements for easy-to-open packaging. To qualify for their highest tier, packaging must pass ISTA 6-Amazon.com testing protocols, be curbside recyclable, openable within 120 seconds with minimal tools, and free from elements like blister packs. Amazon has even started charging vendors $1.99 per unit for products that don't meet their packaging guidelines. The technology exists to make packaging easier to open without sacrificing protection. Laser scoring uses precise laser beams to create controlled perforations that maintain barrier properties while providing easy open functionality. The laser creates a controlled score depth that guides the tear while maintaining protection against moisture and gas infiltration. It works on multi-layer laminates, plastic films, metallized films, and paper plastic composites. Modern laser perforation can create neat tear lines without affecting the sealing performance of the package. The technology is so precise that it can control exactly how much force is required to initiate a tear and where that tear will propagate. It's like creating a planned failure point that activates only when the consumer wants it to. Yet despite these advances, much of the packaging industry continues to prioritize protection and theft prevention over consumer convenience. The engineering that goes into creating these films is genuinely impressive. From a technical standpoint, the ability to control molecular orientation with such precision that you can make a material incredibly strong in one direction while maintaining controlled weakness in another represents decades of materials science research. The next time you're battling with impossible to open packaging, remember that you're not fighting poor design, you're fighting sophisticated engineering. Those polymer chains were carefully aligned by machines that stretch the material hundreds of times its original dimensions in precise machine direction and transverse direction ratios. Multiple layers were precisely laminated together, each with its own molecular orientation designed to deflect tears in unpredictable directions. The $22 billion industry behind tough plastic films isn't going away anytime soon. Food packaging demands barrier properties to prevent spoilage. Retailers need theft-resistant packaging to protect their inventory. Manufacturers require materials that can survive the rough handling of shipping and distribution. But consumer pressure is creating change. The success of Amazon's frustration-free packaging program has shown that it's possible to maintain product protection while dramatically improving the opening experience. More companies are investing in laser scoring and other controlled failure technologies that let you open packages easily when you want to, while maintaining protection during shipping and storage. The science of polymer orientation will continue advancing, but hopefully toward packaging that works with consumers rather than against them. After all, the most sophisticated engineering in the world isn't worth much if it leaves people reaching for kitchen knives just to open their online purchases. Until then, remember that your kitchen can opener is your friend and that the plastic film you're fighting represents some of the most advanced materials science happening today, even if it doesn't feel very advanced when you're trying to open it. Make sure you subscribe.